Okay, welcome back. So, let's take a look at avoid obstacles now. All right.
You are given an array of integers representing coordinates of obstacles situated on a straight line. Assume that you are jumping from the point with coordinates 0 to the right. You are allowed only to make jumps of the same length represented by some integer. Find the minimal length of the jump enough to avoid all the obstacles.
So, I have to say, when I first encountered this problem, it was just the text. The image came later, and I'm so glad it did because, I'm so glad that it exists, is what I'm trying to say. It really definitely helps clarify the problem. So basically, the idea is that we've got this input array. It contains the indices of some obstacles on a number line here. And the idea is that we're making jumps of a particular size, and we want to choose the size of jump that will allow us to clear all of our obstacles. So, this is an interesting problem. And of course, the way we're going to do it is we're going to start with the most brute force, naive, straightforward kind of interpretation of the problem. So we're basically going to look at this and just say, okay, well, we're trying to decide, or we're trying to figure out how big the jumps can be in order to clear all these obstacles. And I think we want the minimum one, right? Yeah, the minimal length of the jump. So let's try that. And yeah, while we're here, might as well take a look at our constraints. So we're going to have as many as 10 obstacles, and they can be as great as 40. The index can be as large as 40. All right, great. So for our jump size, let's do something like this. Let's put the whole thing in a loop. We'll say for let jump size be assigned the value of 1. We're going to start at 1. And then jump size is less than 40, I guess, right? Because we know that there could be an obstacle. Well, it could include 40, so let's say 41. And we'll do jump size plus plus. Let's just do 42 for good measure. Okay, great. So, and in fact, I'm looking at this and I'm thinking, can jump size even be 1? Like, would that be possible? Because if jump size is 1, then we're kind of doing something like this, right? And we're going to cover every single value, which means if there are obstacles, we will inevitably hit every one of them with a jump size of 1. So is it possible that there are not obstacles? Well, no. It turns out we're going to have at least 2 obstacles here. So jump size can't be 1. There's no way it would be possible. All right. So our jump size is going to start at 2. It's going to go all the way up to 41. And the reason I wanted to start at 41 is, or go up to 41, is because we're starting at 0. And if our jump size was just 40, then by doing that jump, we would end up at 40, and there could be an obstacle there. So 41 is basically the largest possible size that our jump could be. And you know what? I'm gonna retool this, because I'm thinking, like, ultimately what we're trying to return at the end here is jump size, right? But that's not going to work right now because jump size is being declared inside of this for loop. So I'm going to say let jump size be assigned the value of 2. I'm going to do that out here. And because I'm doing that out here, I'm starting to think maybe a for loop isn't best. But for now, I'll just leave it like that. Is that going to work even? Can you have a for loop that has an empty part? Like, could we clear this part or clear this part as well? Well, yeah, you can have an empty part in a for loop. It's just going to disregard it. It's going to say, oh, okay, nothing here. We'll move on to the next part. You do have to have the semicolons, though. So notice it's giving us 42. That's basically the size that jump size will eventually reach. In fact, I guess, yeah, I could make that 41 because it's going to iterate, and 41 is definitely going to work. So, okay. We've settled on that. That's looking good. And now, okay, we actually want to test this now. So we'll say for let position be assigned the value of 0. We're starting at a position of 0, and we want, let's see, we'll talk about that later. And then position, well, position plus equals jump size, actually. That's the point of it, right? That's where we're jumping. Okay, and then basically, if we encounter, how should we do this? So basically, if input array dot includes position, right? Because basically, if we're at a position where there is an obstacle, then we kind of want to break out of this and say it didn't work, right? So let's see. Oh, I have an idea, actually. Okay, so let's do something like this. So we'll say let possible be assigned the value of true. And I'm actually going to bring this back inside. I'm actually going to get rid of this next one here, which might seem a little reckless. I'm also going to get rid of this. So the idea now is that the return for this function is going to happen right inside the for loop. That's the plan. So basically, if we get to the end of this and it turns out it is possible, not position, if it is possible, then we're going to return jump size. And that's going to be it. So our return is going to happen in the loop. Everything is going to happen in the loop. Okay, great. So basically, we're inside of our loop. We're starting with a jump size of 2, and we're just going to let it rock until it gets to a point where it turns out to be possible. So if that means it's got to be a jump size of 41, so be it, but it's going to happen within the loop. So because of that, we don't need to tell it when to stop, because as soon as it does this return, well, the loop's not going to continue because the function's over. Like avoid obstacles is done as soon as we hit that return. Okay, so what do we want to do here? Yeah, we wanted to do this. If input array dot includes position, then we want to do two things. We want to say, well, possible is false. It's no longer possible if we're hitting an obstacle. And we don't want to go any further if it's not going to be possible. So we're just going to say break. Okay. And then from there, we need just one more thing, because if we take account of everything here, first of all, we're going to start with a jump size of 2, and it's going to try that out. It's going to say, okay, I'm starting here. I'm going to go over here. Is this an obstacle? No. Okay, I'm going to go over here. Is this an obstacle? No. Okay, I'm going to go over here. Is this an obstacle? Oh, yeah, it is. Okay, well, that's not possible. So in that case, we'll try 3. So let's jump 3. Is that an obstacle? Yeah, it is. So that's not going to work either. So we'll try 4. 4 makes it over there, no obstacle, and then it would make it to 12, and there'd be no obstacle there, there'd be no obstacle at 16, no obstacle at 20, etc. So we need to be able to tell it, well, hey, you got to stop here, you know, like if you found the biggest obstacle, then stop. Okay, so let's do that. Let's determine the biggest obstacle. That's probably actually a good idea for us to do out here. So let biggest obstacle be assigned the value of math.max ... input array. We're doing a spread operator. So biggest obstacle is just basically the last, maybe I'll call it the last obstacle, because it's not necessarily that it's a bigger size, that has a bigger index. So last obstacle. And then basically from here, all we need to check is position still less than last obstacle? Because if we're making it to last obstacle, then we've done enough. Okay, so I guess there is a little bit of this that lives outside of the loop. That's kind of nice. So let's run this and we'll see what ends up happening here, if it's going to pass some of the tests or not. So let's see, it passed one of the tests, and that happened to be this first one. Okay, so that's nice. And then here we're returning 3, and it's saying, no, can't return 3. It's going to be 4. So I wonder why it returned 3. Let's see. So I'm looking at this one, last obstacle. Oh, you know what? It should keep going even if it's equal to last obstacle. I think that's the issue that happened here, because basically it said, okay, jump size is 3, position initially is at 0, add 3 to it. Now position is no longer less than last obstacle. So it wasn't even checking if there's an obstacle there. So we do need to put in the less than or equal to check if it's actually landing on an obstacle at its last step. And with that, it looks like it's working. Okay, so that's kind of nice. Let's try submitting it and we'll see if it passes the hidden test. Maybe there's some kind of edge case we're not considering here that we're gonna have to deal with. And no, that worked. Okay, so great. Well, that feels good. So we're making some progress here. Let's X out of this and we'll see if there's a better way we can think about this. Because I'm looking at it and I'm thinking, I see nested loops. When I see nested loops, I get a little bit uncomfortable because I start to think, well, that looks big O of n squared, you know, it looks like it could be a big O of n squared situation. So we don't want that. That's not ideal. So maybe there's another way we can do this that's going to be a little more efficient. And yeah, there is going to be something like that. So basically, here's how we're going to do it. We're going to make an observation about this problem, okay? We're going to make an observation about it. And this is going to be kind of an interesting one. We're going to use a bit of math here. So I do need to make sure that we're all familiar with a few key terms here. We'll just clear this. And what I want to talk about is factors and multiples. Okay, so just to make sure everyone's totally aware. So 2 times 3 is equal to 6. So we would say that 6 is a multiple of 2 and 6 is a multiple of 3. We would also say that 2 and 3 are factors of 6. So basically, if 6 can be evenly divided by a number, then that number is a factor of 6. If we were to multiply 6 by some other number, other whole number, then what we would get is a multiple of 6. Okay, so factors, multiples, basically multiples are made up of factors. That's the idea. It all has to do with multiplication of whole numbers. All right, so let's go back to this. And the reason I wanted to mention factors here, multiples, is because if we're talking about jump sizes here, right? If we're doing something like this, like this, like this, now we're eventually hitting the 6 here. And that's where we're going to stop because we notice, well, we're jumping 2 at a time and eventually we hit 6. And the reason is because 6 is a multiple of 2. We had 1, 2, 3 jumps here, right? So 2, which is the jump size, right? Jump size of 2, jump size of 2, jump size of 2. So basically 2 times 3 ended up being 6. In other words, 6 was a multiple of our jump size. Or another way we could say it is that our jump size was a factor of one of our obstacles. And that is really the key thing here. I mean, the reason 1 doesn't work is because it's a factor of everything. The reason 2 doesn't work is because it's a factor of 6. The reason 3 doesn't work is because it's a factor of both 3 and 9. The reason 4 does work is because 4 is not a factor of any of these numbers. None of these numbers can be evenly divided by 4 without a remainder. So what we really need to check here is, and I'm just going to bring this stuff back so we can sort of alter the algorithm. What we need to check here is, instead of all this stuff, I'm just going to say, is jump size a factor of any of the obstacles? That's what we need to check. So if jump size is a factor of any of the obstacles, then we're going to return false. If it's not a factor of any of the obstacles, then we're going to return true. So that's all we really need to check. And that means we're not going to need to know last obstacle here because we're going to look at each of these. So we could say something like this. Okay, we'll do it one step at a time. So first, let's use another for loop. So we'll say for obstacle of input array. And I forgot my let again. Let obstacle. Okay, there we go. For let obstacle of input array. And basically what we want to say is if obstacle mod jump size equals 0. So what do I mean by this? Well, I'm saying if we were to take obstacle, so let's say it's 6, and we are to try to divide it by jump size, which we'll say is 2 right off the bat, then basically in that case, 6 divided by 2 would carry a remainder of 0. Since it would have a remainder of 0, well, that means obstacle mod jump size would be 0. So 6 mod 2, that's a percent symbol, by the way, is equal to 0. Equals. So 6 mod 2 is equal to 0 because 6 divided by 2 is 3. It has no remainder. And remember, the modulus operator gives you the remainder of when you do division. Okay, so if that's the case, then it's not... Oh, look at this. I just got 500 coins for nothing. Wow. Guys, what a website we're using here. This is truly gamified learning. Great stuff. Okay, so what was it? I could just do this again, let possible be assigned the value of true, and if this ends up being the case, then possible is assigned the value of false. And I guess we want to break also, so we'll say possible, no longer possible, and so break out of that. And then we'll just say if possible, return jump size, not return true. There we go. So is that going to work? So suspenseful. Let's just get a bit of extra room in here while we're... Look at that. It's working. Okay, so that's great. That's a great feeling. I like that a little better. I mean, it still has a nested for loop, so maybe we can clean that up a little bit. But I like it better than what we had over here. Now, I don't really like this whole possible thing, so I want to switch that up a little bit. So instead, I'm going to say if... and we'll do input array dot filter. So we all remember how filter works, right? Basically, filter is a built-in for arrays in JavaScript, and it's going to take a function as its argument. And basically, the way that function works is it's going to take an element, and if that element has some property, it's going to keep it in the array. And if it doesn't have that property, it's going to boot it out of the array. Now, the way we do this is we return a Boolean. So, you know, we could say something like, if we wanted just the even numbers, we would say something like this. X mod 2 is 0. So when we divide it by 2, we have a remainder of 0. That means it's an even number. So this would just be all the even numbers over here. But that's not what we're looking for in this case. What we're looking for is this. So first of all, what's inside of input array? Obstacles. So that's going to be our input. That's the name of our input for the function. And the question is obstacle mod jump size equal to 0? Okay, so we'll do that filter on our input array. And basically what it should do is it should leave only the obstacles that do have jump size as a factor. Okay, so basically this right here, actually, you know what? Let's do this one step at a time. So let's say let factors be assigned the value of this, right? These are the, or no, those aren't the factors. These are the multiples. Yeah, multiples. So those are basically going to be the obstacles that we're going to get caught on. Oh, whoops, I already did log multiples. There we go. Console log multiples. And then what we want to do is, I guess I'll just comment this out for now, just so we can keep looking at it, but that is not going to affect the code. So console log multiples, and we'll just see what multiples we're getting. And this is basically, oh, this is going to go forever because I didn't put a return or something like that. So yeah, okay, great. So for a jump size, and I really should have put the jump size in here as well. Whoops, my bad. Okay, so basically what we're going to get here is the things that this particular jump size is going to get caught on, the obstacles that are going to be an obstacle. So for a jump size of 2, we found that 6 was the obstacle. For a jump size of 3, both 3, 6, and 9. Oh, I didn't even notice. Yeah, I mentioned that 3 and 9 were multiples of 3, but 6 as well. For 4, there were no obstacles. So really, this should be the one that we're returning. 5 would have an obstacle at 5, 6 at 6, 7 at 7. 8 would be fine. 9 would not work. But anything 10 and beyond would be totally fine. Thing is, we're trying to return the minimal length of the jump that's enough to avoid all the obstacles. So we should go with 4. So basically what we're saying is if multiples.length, length equals 0, then we're going to return jump size. And that is a lot shorter than all this stuff down here. We don't have that possible variable, which I don't really like. So let's see, we'll clean this up. Hopefully it works. There we go. Okay, that passes all the tests. Great. Does it pass all the hidden tests as well? Let's find out. And then if it does, maybe we can talk about how we can improve this. Great. Okay, so that passes all the hidden tests. Now, multiples, maybe that could be kind of a confusing name for some users, just because like it's not really, it's in the language of math as opposed to in the language of the problem itself here, you know. So we could call it something like maybe like something like obstacles that we're getting caught on, something that gets that point across. But the main thing is that, great, that's all we need. So that's, I'd say that's a little nicer. I'd like that a lot better. But it could be even better than that still. There's another built-in that I want to show you guys. So we'll go to the docs over here, array.prototype.every. So basically arrays have a built-in called every. And there's a corresponding one called sum, and it works very similarly, but we'll do these one at a time. So for every, the way it's going to work is take an array, and .every, again, is going to take a function. If that function is true for every single one of these things, then it'll return true. If it's false for even one of them, it'll return false. So here, the function is big enough. We're basically saying, is the element greater than or equal to 10? And here, we're saying, well, are all these big enough? No, these two are not big enough, so .every is going to fail. Even though these other ones are big enough, that doesn't matter. It's not every one of them. Whereas this one down here, they're all bigger than or equal to 10. They're all at least 10, so it's true. Every one of them has that property. Sum works very similarly, except basically this would return true if even one of them is greater than or equal to 10, or I guess strictly greater than 10 in this case. Okay, so the one we're going to use today is every, because if you think about it, that's really the flavor of the challenge we're looking at here. We're trying to say that input array dot every, for every one of these, we want this to be the case, that that it's not a multiple. And then we don't have to worry about this dot length business over here. So that's it. That should be it. So if for every one of these things, the obstacle is not a multiple of the jump size, then we're good. We found the correct jump size in that case. I'm just going to space this out. This isn't really like me to do this, but I am going to put the braces on this one just because I don't want it to be a one-line affair. It gets a little sloppy that way. Okay, so I like this. This is really efficient. We're using .every. Now, .every, I was looking it up, and it does have support. It's as well supported as something like a filter or a map. So I think you can use this one. I don't think it's going to be a problem, but you know, confirm that before you do, I guess. I do also want to mention, I did a bad thing here. Includes, I found out, is not supported. So really, I should not be using includes, or at least you shouldn't use it for a production app or anything like that. What I should have done is index of is greater than -1. Which is kind of old school, and I don't like it as much because it's less semantic than includes, but oh well, you know, until it has support, I guess we'll stick with the index of strategy. Okay, so is this better? Yeah, I think it is. And the reason I'd say it's better is maybe not the one we would imagine, because when I look at this, I'm thinking, well, if you think about what my first criticism of this algorithm was, it was that we had nested loops. We had a for loop within a for loop, and that was kind of, we didn't like that. It felt kind of big O of n squared or something like that. So this one you could say, oh yeah, you don't have nested loops, great. But the thing is, we've got this .every, and that's got to go through input array anyway. So, you know, you could sort of say, isn't that kind of the same as a nested loop? And yeah, good point. It kind of is, but it kind of isn't too. And the reason I say that is because basically this one was actually iterating the position. So the position was just increasing. It's just increasing the position. And again, it's not going to be an issue for these kinds of numbers, but let's say that there was like an extra few zeros on the end of these, you know, so maybe it's a really big number and maybe the numbers here can be outrageous as well. So basically now we're talking about a situation where you can have lots of obstacles and the obstacles can be really spaced out. Let's just put another one on there. So 400,000. Now we would really start to see the differences in these two algorithms. And the reason I say that is because this one down here, this loop right here, so this for loop position is basically, it's going to keep going until it gets to the biggest obstacle, right? The last obstacle. So if the last obstacle is 400,000, this loop is going forever. And especially if we were talking about a situation that was like this, where you can only have 10 obstacles, but they could be super spaced out and they could be very large. Well, then this is really going to be the worst algorithm, because basically if we compare it to the other one up here, we find that this one, because it's doing a dot every on input array, it doesn't matter how big the obstacles are. It only matters how big the array is. Okay, so if it turned out that the array, like there could be tons of obstacles, but they could only be, a certain size, well then maybe the other one's better. But if it turns out the obstacles could be very large, but there aren't that many of them, then definitely this is the better algorithm up here. But I mean, with these constraints, which one is better? Well, maybe I'm biased, but I really like this one because it's very mathematical. I like the idea that we sort of got into this discussion about factors and multiples. So I would probably say I like this one better, but look, it's up to you. If you have a preference, follow your heart, I guess is what I'm trying to say. All right, did we submit this one? Have we finalized our solution here? I think we did, but yeah, just in case. Okay, so if you want to take a look at this solution, it is number 6261 for avoid obstacles, which is task, 22. Okay, great. So nice job on this.